Hello friends, welcome back to Edupedia Word Videos, your destination to free online education. In this video, we will be discussing fundamental theorem of arithmetic and its use in calculating LCM, HCF and various other problems. But first of all, let us discuss composite numbers. Friends, a number which is divisible by number or numbers other than 1 and the number itself is said to be a composite number. Say for example we have two numbers as 15 and 11. Clearly, if we divide 15 by 15, we will get 15 into 1 and the remainder 0 as one of the equation. And if we divide this 15 by 1, we will get 15 as the quotient and remainder again 0. But if we try to divide 15 by some other numbers, say by 5, we will again get the quotient this time 3 but the remainder again 0. That is 15 is divisible by 5 also. Now if we try to divide 15 by 3, we will get the quotient as 5 and remainder again 0. Thus this number 15 is divisible by 15, 1, 5 and 3. Now let us have the number 11. It can be expressed as 11 into 1 as well as 1 into 11 plus 0 if we apply the Euclid's division lemma. That is, if the divisor is 11, the quotient is 1, and if the divisor is 1, the quotient is 11. But if we try to divide this 11 by some other number than 1 and 11, then this 11 will not be divisible. Such a number is called a prime number, whereas the number 15, because of these two additional factors, is called a composite number. Thus, this number 15, no doubt it is a composite number, that it is divisible by some other numbers, but it can be expressed as a product of primes. That is, if you have expressed it as 15 into 1, then this 15 can further be expressed as 5 into 3 into 1. So, this 15 can be reduced to these value or this product, which is the product of primes. Now let us have one more example. Say a number 220. Clearly it is also a composite number, because since it is having a 0 at last, it will be divisible by 10. So it can be expressed as 22 into 10. But this 22 can further be expressed as 2 into 11, and 10 can be expressed as 5 into 2. So again all these numbers are prime in nature. Thus this composite number is again expressed as a product of primes. In fact, if we have a larger number, say 1980, which will surely be a composite number because it is also having a 0, so it will be divisible by 10 also, which will account for its nature to be a composite number. We can have a factor tree of this number, as if we divide this number by 2, we will get 990. Again, on dividing 990 by 2, we will get 495. On dividing 495 by 3, we will get 165. And on dividing again 165 by 3, we will get 55, which can further be expressed as 5 into 11. So this composite number is again expressed as a product of primes. That is 1980 is equal to 2 into this value, which can further be reduced to 2 into 495, which can further be reduced to 2 into 3 into 165, and this 165 can be reduced to 3 into 55, which will be reduced to 5 into 11. So we have seen that every composite number in fact can be expressed as a product of primes. This is also known as the fundamental theorem of arithmetic. Formally, this fundamental theorem of arithmetic says that every composite number can be expressed as a product of primes, and this factorization, that is expression of these composite numbers into the product of primes, is unique. Apart from the order, in which the prime factors occur. That is, say we have a number 30. We can express this 30 first as 5 into 6. Now this 6 can be expressed as 2 into 3. Thus, we get a product of primes. Somehow we can also express it as 2 into 15, which will reduce to 2 into 5 into 3. Similarly, we can also express it as 3 into 10, by which we will get 3 into 5 into 2. Thus, in all the three expressions, we are getting the same primes, but their order is different. That is, here 5 is at the first place, here 2 is at the first place, here 3 is at the first place. Similarly, there can be some more orders also, but the value of primes in these products is unique. That is 2, 3 and 5. Generally, to avoid so many expressions of a given composite number, we write this prime factorization in such a way that the prime factors are occurring in an ascending order. That is, first of all we will write 2, then 3 and then 5. Now friends, since by the fundamental theorem of arithmetic we have come to know that for any given composite number this prime factorization will always be unique, and we have decided that the order of these prime factors should be in an ascending order. So there are many ways to get this prime factorization. Either we can divide this number by the lowest prime, that is 2, and get the quotient, then divide this quotient by again the lowest possible prime with which it is divisible. Since it is not divisible by 2, we will divide it by 3 and get 5 as quotient. So 5 is also prime, so we will have the prime factorization as this. Or we can also proceed by decomposing this composite number as a product of one or more composite numbers, say 6 into 5, where 6 is composite and 5 is prime. Since the ultimate prime factorization will be unique, so this composite can further be factorized as the product of primes, and we will get the same result. Now friends, let us discuss how to calculate LCM and HCF using prime factorization. Friends, to calculate the HCF of two numbers, say A and B, as well as their LCM, first of all perform their prime factorization. Then the HCF will be the product of the smallest power of each common prime factor in the two numbers, that is A and B. Whereas LCM will be the product of greatest power of each prime factor involved in the numbers. That is, the difference in the two values is that here we need to take the smallest power of the common prime factor, whereas in LCM we need to take the greatest power of each prime factor involved in the numbers. So let us have an example to calculate the LCM and HCF. Say we have two numbers 30 and 84. The first step is to calculate their prime factorization. Now 30 can be written as 2 into 3 into 5. Thus their powers are 1 for each of these prime numbers, whereas 84 can be written as 2 into 42. This 42 can further be written as 2 into 21, and 21 can be written as 3 into 7. So these are the prime factors involved, and we have 2 into 3 into 7 as the prime factorization of 84. So if we combine these two as some form where we denote these two numbers by some power, that is 2 raised to power 2, we will get this expression. Now HCF is the product of smallest power of each common prime factor. Now the common prime factors are 2 and 3, and their smallest powers involved in both are, here we have 2 raised to power 1, whereas here we have 2 raised to power 2. So the smallest power is 1, and 3 is having the power 1 in both the cases. So the product 2 into 3, that is 6, is the HCF of the given numbers. Regarding LCM, it is the product of greatest power of each prime factor involved in the numbers. Now we need to consider each of the prime factor involved in both the numbers. So all the prime factors involved are 2, 3, 5, which is involved in first number, and 7. And their greatest powers are, 2 is having the greatest power as 2 in the 84 number, 3 is having the power 1, 5 is also having the greatest power 1, similarly 7 is also having the greatest power 1. So the LCM will be 2 raised to power 2, which is 4, into 3, that is 12, into 5, which is 60, into 7, which is 420. So for the numbers 30 and 84, HCF is 6, whereas LCM is 420. Let us have one more example. Say we have two numbers 24 and 96. Clearly 24 can be expressed as 6 into 4, and their prime factorization will be 3 into 2 and 2 into 2. Since the prime factorization of these composite numbers will be unique, so the prime factorization of 24 will also be unique, that is this expression. So 24 can be written as 2 into 2 into 2 into 3, that is 2 raised to power 3 into 3. Whereas 96 can be written as 12 into 8, and this 12 is 4 into 3, whereas 8 is 2 into 2 into 2. This 4 is further reducible to 2 into 2. So we have the expression of 96 as 2 into 2 into these 3, 2 into 3. So 2 raised to power 5 into 3. So HCF will be the product of lowest power of the common primes. Clearly the common primes are 2 and 3, and their lowest power is 3 and 1. So the product, that is 2 raised to power 3 is 8 into 3 is 24. So the HCF is 24 for the numbers 24 and 96. Now let us talk about LCM. For LCM, we will include all the primes. Only 2 and 3 are the primes in both the cases. Their highest power is 5 and 1. So this product will be at LCM, that is 2 raised to power 5, which is 32 into 3. So the value 96 is the LCM of the numbers 24 and 96. Friends, in this case we can see that the product of the numbers given are 24 into 96, whereas HCF into LCM is also 24 into 96. That is, both these values will be equal, and their value will be 2304 if calculated. Now if we consider the previous example, let us see if there is a relationship in the products in this case also or not. The product of the given numbers, that is 30 into 84, is 2520, whereas HCF into LCM is 6 into 420, which is 2520 again. So again this value is same, that is the product of the given numbers is equal to the HCF into LCM. In fact, this is true for any two given numbers. So friends, for any two given numbers or positive integers, since we are taking only the positive integers in our examples, for two positive integers, the product, say the integers be a and b. So for any two positive integers, say a and b, their product, that is a into b, is equal to their HCF multiplied by their LCM. So if we know the values of any two given numbers and it is also given that their HCF is some value, then you can calculate LCM by using this formula, that is LCM will be given by a into b over HCF. Similarly for the HCF. Now let us have one more example where we need to calculate the LCM and HCF of three numbers. Let the numbers be 4, 12 and 100. Clearly 4 can be expressed as 2 into 2 or 2 raised to power 2. 12 can be expressed as 4 into 3, that is 2 raised to power 2 into 3. Hundred is 10 into 10 or 5 into 2 into 5 into 2. So it will be 2 into 2 into 5 into 5 when written in ascending order, the expression for prime factorization, which will give us 2 square into 5 square. So for HCF, for the numbers 4, 12 and 100, we need first of all the common prime factor, which is 2, because 4 is having only 2 as the prime factor and this 2 is included in 12 and 100 also, and its lowest power in all the cases is 2. So HCF is 2 raised to power 2, that is 4. Now regarding LCM, it is, first of all we need to have all the prime factors involved in any of the given numbers. So the prime factor involved are 2, 3 and 5, and their highest powers are 2 has highest power as 2, 3 has the power 1 only in 12 and there is no 3 in any other numbers 4 and 100, and 5 has highest power as 2. So the LCM is 4 into 3 into 25, that is 300. Friends, if we product these three numbers, we will get 4800. Whereas if we product their HCF and LCM, we will get 4 into 300, that is 1200. Clearly these two values are not equal. So the statement that product of the given numbers is equal to their HCM into LCM is not valid in case of three numbers. That is, A into B into C is not equal to HCF of A, B, C into LCM of A, B, C. Now friends, let us discuss another concept on this theorem. Friends, you may be asked to check if the number 6 raised to power n can end with the digit 0 for some natural value n or not. Friends, if a number ends with the digit 0 at its units place, that is at its end, then this can be factorized into 21 into 10. This 10 accounts for this unit 0. Thus, this 10 has the prime factorization as 2 into 5. So in other words, if a number is having 0 at its units place, then its prime factorization must have the prime numbers 2 and 5 because of the fundamental theorem of arithmetic. Because since these 2 and 5 are prime factorization of 10, they must also be the prime factors in the prime factorization of 210. Now, in the case of 6 raised to power n, 6 can be written as 2 into 3 in prime factorization form. So this number can be rewritten as 2 into 3 raised to power n, or 2 raised to power n into 3 raised to power n. That is, for the value of n to be 1, this value will be 2 into 3. For n to be 2, this value will be 2 square into 3 square, that is 2 into 2 into 3 into 3, and so on. Clearly we can see that for any value of n, we cannot have the prime factor 5 in the prime factorization of the number 6 raised to power n. No doubt we can have 2 in the prime factorization, but the combination 2 into 5 will yields 10, and thus 6 raised to power n can never end with the digit 0 for some natural value n. Friends, these were some concepts on fundamental theorem of arithmetic. Thanks friends for visiting edupediaword.com.